And now I'm pleased to introduce Dimitar Sasselov, a professor of astronomy at Harvard and the director and founder of the Harvard Origins of Life Initiative. Professor Sasselov's studies focus on finding the starting points of life on Earth and elsewhere. As he discovers new planets that might host life, Professor Sasselov is giving us more information about our own origins on Earth. His new book, The Life of SuperEarths, How the Hunt for Alien Worlds and Artificial Cells Will Revolutionize Life on Our Planet, examines the age-old question, is there anyone else out there in the universe? In looking for super-Earths, rocky planets that resemble Earth and orbit other stars, scientists have found planets made up of mixes of elements different from our own. With this knowledge, they can attempt to create novel life forms sustainable by these other planets. This confluence of innovation in astronomy and biology allows us to begin to peer into the unknown. Before I turn things over to Professor Sasselov, I'd just like to thank you for buying books from Harvard Bookstore. By doing so, you're supporting an independent business and ensuring the future of this author series. Please join me in welcoming Professor Dimitar Sasselov.
Thank you all for coming. Thank you very much for a nice introduction. I want to make this a very Cambridge-like book reading, unlike what most scientists like me would rather like you to go through is a long PowerPoint presentation. Instead, it's going to be mostly me telling you a few things, trying to provoke you, and then engaging you, I hope, into a conversation, which I would like to spend most of the time doing. Now, why I'm here today is because I got both involved but really excited, motivated by two developments, and I would call them game-changing developments in science. One in astronomy, the other one in biology. And their unlikely marriage, bringing something new which is about, and I believe so, is about to change not only the life of a few scientists, but everyone's life. That is what is the motivation between my book. And let's start with the planets first, with the astronomy. That's one side of the equation. This book is indeed about super-Earths. And there is something in the title, The Life of Super-Earth, which is a double meaning that I would like to come back to. So what is a super-Earth? It is a term which we scientists use to describe a planet that is not in our solar system. So it is a new type of planet. It is a planet that is larger than the Earth by a factor of 2, maybe in terms of mass, it's up to maybe 10 times more massive than the Earth. So not much bigger than the Earth. Certainly in that gap, if you will, in our own solar system between the big giant planets on one side and the smaller, what we call terrestrial rocky planets on the other. So, you know, the Earth, Venus, Mars, and Mercury, the smaller rocky planets, and then you have the gas giant planets. But in between, there is a gap. It is a gap which is actually quite large, both in size and in terms of mass. There is nothing there. The Earth is the largest rocky planet, and then Uranus and Neptune, which is almost the same size, are the next coming over, and they're giants. They're more than 10 times, actually 15 times more massive than the Earth, and they're more than 3 times, almost 4 times larger in size. So they're a different kind of beast. Now, what has happened in the last few years is we, the astronomers, have been looking for planets around other stars. And our dream of 450 years, it started with Copernicus, when people first realized, the Earth is not the center of a frame of reference where everything else moves somehow around it. The Earth is one of those points of light which are planets. It is also a planet. And the Sun is the center of reference. And the Sun actually is a star. So the other stars should have similar planets orbiting them, and probably even planets like the Earth. So this was a logical conclusion, which people came about to just about 450 years ago. So they started looking for those planets, and they didn't find them. People were looking for them very actively in the 20th century, And they found them, but it was a mistake. There were several cases in which they were announced and then they had to be retracted. So when in 1995, my wife and I were actually in Florence in our honeymoon, and I was doing work in parallel, going to a conference there. I knew a colleague of mine who said, well, I have a big announcement tomorrow, and I have this poster which gives you a hint about what it is going to be about. And what it was about is the first planet orbiting a star similar to the Sun. And I asked him, well, you don't tell us here what the planet is. And he said, oh, it's like Jupiter. He said, well, what about the orbit, the orbital period? And he said something, and I went back to the hotel that night and said, sure, this is probably another one of those false starts. He said that the period of that Jupiter around that solar type star is about 400 days. And that's too short. Our Jupiter takes 12 years. And we had a very good theory, which had been cooking for 300 years, why Jupiter should have a very long period and why the Earth has a short period. Earth goes around the Sun in 1 year, Jupiter takes 12. Small planets form next to the star, big planets have to form away from it. You can't have a Jupiter at 400 days, which is essentially like the period of the orbit of the Earth. It just doesn't work that way. So I go the next morning, the press is there. It was a big deal, you know. And he gives the talk, and I'm sitting just right in front there. And his first slide is, we have evidence that there is a planet around the star 51 Pegasi. His second slide is, and the orbital period of the planet is 4 days. 4 days. So this taught me some neurobiology. And the neurobiology I learned is that the brain processes the stuff that we hear. I'm sure the previous night, Michel Mayor, who was the astronomer who discovered, together with Didier Queloz, the first planet ever around a normal star, I'm sure he told me 4 days. In fact, he told me afterwards, yes, I told you 4 days. I didn't tell you 400 days. And I know that I thought it was 400 days. So I hear 4, and my brain makes it 400. So that's what I mean by if you're so predisposed in your thinking, if you're prejudiced, if you want, as a scientist, that the theory just doesn't work, you can fool yourself to that point, from 4 to 400. And I know I was fooling myself because I told it to Sheila, and Sheila remembers. So I was not fooling myself 2 times. So I didn't make it up. Anyway, this was a big discovery for everyone, but this was particularly, and the reason I'm telling this story is not only to make it personal, so that you see where I'm in that whole world of exoplanets and how I got into it, but particularly because what we discovered and what we are still discovering, a lot of surprises. We had one example of a planetary system, our own solar system, and we had it for a long time, and we had thought about it for a long time, and there were a lot of things which we had gotten wrong because we didn't have a second example or more examples. And it's a very cautionary story when it comes to science, but particularly for what I'm trying to tell you today, because then I'm going to another case where we have a single example. Can you guess which one that is in science as the big questions? Life, yeah. We only know of one example of life, one living planet, and this is our own. So that, just bear this in mind when I try to sell you a bridge between the two, between biology and astronomy. At least on one hand of the bridge now, we have more than one example of a planetary system. And one of the big surprises was that, yes, indeed, we found a lot of planets which are in between the size of the Earth and the size of the giant planets. And that's what the title is, the SuperEarths. Now, what we find about them, and mostly literally in the last 2 years, and literally in the last few months, so they're not even all in this book, because it was already in the press, is that these planets, the SuperEarths, are more plentiful than we even anticipated. The fact that there is none in our solar system is just a matter of chance. It just happens so. In fact, there is one in our solar system, and that's the Earth. And maybe Venus almost didn't make it into the family, but the Earth in that classification is just a smaller sibling in the larger family of those super-Earths, which are 50% larger, maybe 2 times larger in size. So that's the family we are talking about. Now, the reason I call it family is because those planets, indeed, at least some of them, could have very similar, if not identical, characteristics to the planets like our own, the Earth. In other words, they are rocky, they may have some water on the surface, they may have an atmosphere which is relatively thin. They have no resemblance, those ones, no resemblance to the gas giant planets, which is just a lot of gas, maybe with a core inside, but no solid surface, which in any case can be identified. And they also turn out to be different from the really small ones. And when I say the really small one, I mean things like Mars, planets like Mars, which are just a little bit too small to retain an atmosphere, to have active volcanoes, and to have exchange between all that rich chemistry of the interior, which every terrestrial planet has, and its surface. And you will see that's an important point when it comes to life and the connection between the planet or planets and life. Now, people ask me, so why super-Earths? Where is the super come from? And I'll read you something from the book, because it relates to things which happened here around Harvard Square and how this whole thing came to be, and it's very typical in science. So we're going back to 1999, when a group of us, mostly at the Harvard Smithsonian Center for Astrophysics, and mostly observers and engineers, came together to propose to NASA an innovative space telescope design for planet detection with a square mirror as opposed to a round one. A square mirror like this with edges rather than a round one. My colleagues Kostas Papaliolios and Peter Nissenson had invented this unusual design in order to minimize stellar glare and allow glimpses of planets huddled close to their stars. With a team of about 20 and led by our experienced space mission scientist Gary Melnick, we prepared a detailed scientific and engineering proposal. My job on the team, as a younger fellow at the time, was to work out what kind of planets our telescope might be able to discover. It seemed then that super-Earths were in reach of this new telescope. I like to call them super-Earths and super-Venuses for short, as it had been common in astronomy to use the adjective super for newly discovered or hypothesized objects that are larger in size or energy than known ones. For example, stars are larger than giant stars. Stars that are larger than giant stars are called supergiants. Explosions that are stronger than novae are called supernovae, and so on. The shorthand stuck, as you've probably already surmised, although our proposal for this new innovative telescope was not accepted by NASA. But what happened is another one was accepted by NASA, and that was the so-called NASA Kepler mission, named after Johannes Kepler, one of the big followers of Copernicus, and one of the people who predicted that planets like Venus and Mercury will occasionally pass between us and the sun, and we'll be able to see their projected disks on the shiny surface of the sun. And he in fact predicted that there would be a passage like this for Mercury in 1631, which indeed happened. Unfortunately, he died literally months before that first passage was observed, so he never managed to see a transit. Then, just a few years later, in 1639, the first time the passage of Venus occurred, as was observed and documented by a couple of astronomers in England. And then started this big scientific exploration of what these passages could be used for. Turned out that this is a great way to triangulate your distance to the sun. And that's very important if you want to use the stars for navigation. So if you want to have good navigation, like the British fleet certainly needed that, you needed to know the distance between the Earth and the Sun very well. And Venus was the way to do it. Of course, the French and the Russians figured this out very soon too. So there was a lot of scientific and more than scientific competition going on when the next set of transits occurred. That was when Captain James Cook was tasked to do this, to observe the transit of Venus. And by the way, he discovered places like New Zealand and so on. This is also when people like, what was it? Some of the famous people from the creation of the state lines here in the United States. Charles Mason and Jeremiah Dixon. Anybody knows who they are? Yes, this is the famous Mason-Dixon line, Mason and Dixon. Well, you know how they started. They started as astronomers who were chasing the transit of Venus. And then they came down here to work on what we call now the famous Mason-Dixon line. So these transits, as important as they were at the time, turned out to be the best way today to discover planets, and particularly small planets. So what we proposed 12 years ago to NASA with the Kepler mission was, let's use those transits of planets as they pass in front of their parent star very far away as tiny eclipses, as tiny dimming of light which occur regularly, periodically. Let's use them to discover new planets. And it worked marvelously. In the last, Kepler has been now up in space almost 3 years. It's a space telescope, a big camera. And it has by now discovered more than 2,300 candidate planets. We've already confirmed almost 40 of them, and it's counting. We're finding a lot of them. But what is more important, and particularly important for my story here, is that there was a threshold which was crossed 2 months ago, in December last year, was when finally our technology caught up with our dreams of discovering a planet the size of Earth orbiting another star. And its name is Kepler 20F. It has a number, like most of ours planets. People ask me, well, why don't you call them after pretty names? Well, we have 3,000 and counting. We will run out of names pretty fast, so we decided numbers are safer. So we hide behind boring numbers. But Kepler 20F, I think, will remain in its history as the moment when we managed to achieve that experimental scientific threshold of being able to discover and study a planet the size of Earth. This planet is very far away, but 1,000 light years from us. It's in a system, Kepler 20, with 4 other planets so far, and probably more, just like our own in some sense, but different in many ways. It is a warm planet, so we wouldn't say it's Earth-like, because its temperature is more like that of Venus than of Earth. But nevertheless, we now know that it's just a matter of time, and that matter of time is next year, or maybe later this year, that we will have more of them, and particularly ones which are in the habitable zone, as we call it, that is at distances from their stars where the temperature is comparable to what we have here on Earth. So in a certain sense, we've completed the Copernican revolution. We are actually now finally done the part that astronomers are supposed to do, which is to shift, and it is a historic shift, mind you, to shift the question about life in the universe from the astronomy side of things, which is, are there environments, are there places in the universe, in our galaxy at large, where life could possibly emerge and sustain itself? And it seems now that astronomy is about to answer and practically answer this question. And the answer is yes. So the shift is now to biology, because now the question is, what does it take for life to emerge? And once we are able to answer that, then we will know our place in the bigger universe. And that brings me to the second part, which is the question, indeed, what about life on other planets? And this is where the main motivation for this book is, because there is a development coming from the other side, from biology, which now, in a synergy with what we are doing in planetary science, could potentially bring us there. And that development is our ability to know what we are looking for. And that may sound a little bit too much for those of you who know that we don't have a definition for life. A lot of definitions, nobody agrees on the same definition. Essentially, we don't understand what the basic nature of the phenomenon life is. And here I really would like to keep it as simple as possible from a scientific point of view, meaning life equals biochemistry. That is, let's talk about the chemistry of life. And that chemistry, which we call biochemistry for short, is very specific. There is a big world of chemistry out there, meaning there are many different molecules, there are many different chemical reactions. And life somehow has decided or chosen a very small group of them and a very specific set of reactions. And those networks is what we see as life today, here on this planet. So if you think of it as a landscape, the chemical landscape, with all the possible molecules, chemical reactions, initial conditions, there is a very large peak somewhere in it, at the top of which is the biochemistry of Earth life. And the big question is, are there other peaks out in this big, vast landscape? And the other part of the question is, if they are, how do we know? How do we find them? How do we look for them? You could enter that landscape from many, infinitely large almost, number of entry points. And we've been trying to do that for all intents and purposes. That's what chemists do all the time. But because it's such a vast landscape, that seems like a futile effort, going blindly and looking for other peaks of high molecular activity, which is what biochemistry on Earth is. So what we are thinking instead is, why don't we try another approach? Of course, you could take the approach of being on the peak itself and walk down. Like there was a Russian poet and songwriter 30 years ago who talked about the gods who decided to walk down the mountain to the valleys. We can try to do that. We've been trying to do that. Biologists have been trying to do that for 40 years now, since the DNA structure was discovered. And we've basically failed completely to understand where those valleys are, which take us out to the entry points into the landscape. Meaning, in other words, the origin of life on Earth. You can't deconstruct it, it seems, because even the simplest microbe with the smallest genetic material, with the tiniest DNA, is a very sophisticated creature, it turns out. So we failed, but we learned something. And what we learned, that every little living form on this planet has a heritage, and that heritage is almost 4 billion years long. And that some of that heritage is in its tiny DNA, and somehow remembers the geological trials and tribulation of its predecessors. And it has survived, obviously. It's part of that tree of life. So it does have predecessors. It didn't just pop out of nothing recently. And that's true for each one of them. And that's why we can't go back, because there is a huge gap between even the simplest microbe and what might have been what we would call the emergence of life, or the origin of life. So what people are realizing now, and that's partly motivated by these discoveries in the astronomical realm, is to go the other way, bottom up. Let's try to find and build from scratch molecules which have the same functions as we know and love for life. Molecular systems that make copies of themselves, molecular systems that use energy maybe from the sun or from something else to do something and to self-sustain themselves in a cycle. And this is where, in a very interesting way, what we learn about those distant planets comes back to inform the work in the lab. What we learn about those distant planets is that the ones which are similar to the Earth, and we believe now the whole family of Earth-like super-Earths, rocky planets, although they're bigger, have enough energy in their interior that all that rich chemical reservoir which is inside the planet can filter through the crust of the planet and reach the atmosphere and the surface. And usually that happens in terms of some kind of chemical cycle. We call them global geochemical cycles because they affect the entire planet. You definitely have heard about the carbon cycle. This is an example of a global geochemical cycle, which nowadays on our planet is co-opted very significantly by life, and more recently even by us as representatives of one tiny part of this tree of life. But more importantly, it can operate on its own without life in a completely inorganic way. So this is the connection, those kind of cycles which are possible on rocky planets, and what kind of chemical information they give to those of our colleagues in chemistry and biology that are trying to design what we call a minimal cell based on information from scratch, that are trying to find those additional peaks in the chemical landscape which hopefully reside close to the entry points which correspond to other planets out there. Not planets in our own solar system, because our terrestrial planets, Mars, Venus, the Earth, Mercury is too small to even talk about any of that, have a geochemistry and geology which is very similar in their general terms. While we expect that those super-Earths, some of them will have different cycles. And that is the connection between them, that we hope one day will actually bring the two parts of the bridge building together into that seemingly unresolvably large gap between what we see today on Earth as a very sophisticated biosphere with a very long heritage, and what we see exists on planets and the cosmic environment simply as a combination of chemicals and molecules and environments, and understand it as possible origins of life, whether they are with the same universal biochemistry, which we see already here on Earth, but remember the cautionary tale of one example, or whether biochemistries are really dependent on the initial conditions, in other words, on the environments. They're contingent on the environments, and hence there are many alternative biochemical systems in that landscape. Why this is a big deal beyond science is because the synthetic tools which are being developed by the chemists and biologists to build that minimal cell, that simple replicating system, which is in essence a chemical system, but has that function which we ascribe to life, is because this reminds us very much to what happened about 150 years ago at the dawn of organic chemistry, the development of the synthetic organic chemistry tools, which we use and have used for the last 100 years, from the synthesis of medicines like aspirin with Bayer, which was one of the companies which took initially, applied that new knowledge about organic chemistry and its synthetic tools to everything from plastics and what the chemical industry does today. So you have a similar step, but in a completely different level now, where you can think of materials which have some of the functions which we only ascribe to living organisms today, but in fact are just chemical products. This is where you can see some of the practical applications. But where this is bringing us is more importantly to a new realization of what the Earth is as a planet in the bigger family of similar planets around other stars, that it is not necessarily unique, and that life is more of the Earth as opposed to on the Earth, and hence the title, the life of super-Earths, just like the atmosphere of Earth. We don't say the atmosphere on Earth. It is truly a planetary process. Life is a planetary process, both in its emergence and in the way in which it sustains in the planet. And in a sense, once it has emerged and taken hold, the planet and its life have the potential for eternity, apart from the time scales of the star, which is limited by nuclear physics. And this brings me back to my perspective, the perspective of an astronomer, which is partly just in the cold numbers and partly in trying to comprehend those incomprehensible scales of how small the biosphere is and how large the general universe that we know of today is, and how the two are compatible or not compatible, if you will. So I'm going to read you something which relates to that and of my personal experience, because I can't explain it simply by numbers. So this happened to me when I was in high school. So when I was in high school, I had a small telescope. My father had shown me how to use it, mostly during the day. I was on my own at night, spending hours out in the backyard. The place where I grew up was small, no telescope or observatory at school, no planetarium to visit nearby. So I had almost no idea what I would see through my small telescope. Sure, I had read books, some with pictures, but the view through the telescope was something else. The experience was truly visceral. Shivers would run up and down my spine every time I pointed the telescope at a patch of stars. Eventually, the feeling went away, fortunately, but I still remember it. As I looked at the darkness between the stars, I felt as if I could fall into it, like a fear of heights in reverse, like an upside-down vertigo. Perhaps I had read one book too many, and I was imagining things too vividly. After all, I had read about the vastness of the empty space between the stars in my books. But if we had a feel for how big the universe is, we would have permanent shivers up our spines. To stay sane, astronomers use math, lots of it, and this can ruin even the best party, as you know. Seriously, though, this is a way to deal with the problem. Since the time of Eratosthenes in ancient Greece, who measured the size of the Earth, humans have used math and geometry to take the measure of the universe. Almost always, the new knowledge increases our feeling of wonder, and many scientists, and I'm one of them, will tell you that this is why they do what they do. Now, ironically, this vastness, as unfit as it may be to our tiny scale, may be essential for life to emerge and survive. And this was a realization which came to me while I was writing this book. In fact, I talked to one of my mentors here at Harvard, Andy Knoll, and he said, you should write about this. And the realization to a scientist, an astronomer, looks very simple. What happened in the last 20 years, you see, is we managed to see what is called the cosmic microwave background. This is the time in the history of the universe and the place beyond the furthest galaxies when there was just relatively hot gas made of hydrogen and helium, and no stars and no galaxies. It's one of the earliest times in the universe that we can actually see with our telescopes. It's called the cosmic microwave background, and we literally see it. It is not a theoretical construct. It's already gotten 2 sets of Nobel Prizes. So it is a serious development in science as a whole, but how does it connect to what I'm trying to say here? That gave us the point which we needed when James Cook and others went and measured the transit of Venus. We can triangulate, and in this case, we can triangulate the size of the universe in which we live, the observable universe, and we can triangulate also in time because light takes time to come here. So we astronomers is the only archaeologists who see history as it happens back there. And in fact, we don't know the present ever. We only see the past. But what we see is, regardless of what we know or don't know mostly about the Big Bang, what is important is that we have a scale between the time there were the first stars, the first galaxies, and more importantly, the first planets around stars, and today, the present day. And what we see is that it took some time for the first stars to form. Then it took a couple of generations, more than a couple of generations of stars, to produce those heavy elements, because the early universe only had hydrogen and helium, and a very tiny bit of lithium, but hydrogen and helium, that's it. And then it took generations of stars to produce what we are, the carbon, the iron, everything that makes a planet, especially a solid planet. So then you're down to just 7-8 billion years ago. I'm saying just, but our heritage is 4 billion. Our Earth and Sun were formed 4.6 billion years ago. So we live in a very young universe. And what I mean young is because the universe has a future which is way, way in the future. Why? Because now we know what this universe is made of. As you know, it's only 4% us. The rest is dark matter and dark energy. So we can actually take that knowledge of the past and project it into the future. And if we know that the universe so far has existed for 13.7 billion years, we know that the present state will essentially remain the same for the next 100,000 billion years into the future. There is just nothing else to change that dynamic state of the present universe. There will be galaxies, there will be stars, more stars will form, more planets will form. Even more interesting, we saw and we see how the stars are forming as the first stars start and form very quickly, peak, and now slowly slowing down in formation of new stars. The planets are still forming and peaking. So we see a future which is kind of the middle age, the long middle age of the universe. And we are in the beginning of that process. We know we are in the beginning of that process. And by we, I mean this biosphere, this planet, this solar system, this galaxy. What this means is that if life is indeed a chemical process, which is a planetary phenomenon, and which has its roots in the chemistry of that planet, this is of the first generation. We are of the first generation. And I use here generation in the same terms in which we use it in human terms. Doesn't mean that this is a cohort of peers who all got born in 1958. It has a range, but what is more important, they all share something very substantial. And what this phenomenon, if it exists on other planets in this galaxy, and I do think that's probably true, then all of those trees of life that led to what we have on our planet and hence on other planets have chemical roots. It may seem like a trivial conclusion to you, but that actually could not be made 40 years ago because we didn't know the dynamical state and its history of the universe in the terms in which we know it today, and particularly not the chemical aspect of it. And so the question is then, shouldn't we go back to the lab and try to sort this all out with the help of our friends, the chemists? Why do we need to go to those other planets? And you should read the book to see why I think that's true, but the answer, honestly, is I don't know. And so I'll tell you what my speculation or hypothesis about this is. Today we stand on the threshold to new worlds, planets that we could call home, planets that someone else might call home already. The search for them has spawned a new space race, the race to discover an Earth twin planet. The zeal and effort going into this race may seem odd and unjustified. Even for scientists, there is no overwhelming benefit in discovering an Earth twin, because to study the properties of Earth-like planets, they could rely on bigger ones, which are much easier to find and study. Yet everyone agrees that this is a historic moment. What gives rise to the extraordinary excitement of this race is the human yearning for meaning and belonging. It is the 21st century version of the age-old question of the other, but on a grand scale. The question of the other is about how a conscious human being perceives his own identity. Who am I and how do I relate to others? It arises front and center during first encounters. Human history is full of first encounters. Homo sapiens encounters Homo neanderthalensis somewhere in today's Europe. Mayans encounter Spanish conquistadors in Central America, and so on. The time of first encounters on our planet is now over. For better or worse, we humans, all of us, know about each other. The present generation of Homo sapiens has a global awareness, a sense of social connectedness, and an understanding of a common genetic makeup. The end of the 20th century marked a real watershed in this sense. So, the discovery of new worlds orbiting distant stars offers a fresh opportunity to contemplate the first encounter. As in the past, humans approach it with both unsatiable curiosity and fear, with mixed, very strong emotions. As in the past, amazingly, despite all our modern technology and the visions of Star Trek, the new worlds have just begun to uncover, are enshrouded in mystery and full of surprises. And we will never stop exploring, as T.S. Eliot famously wrote. We must never cease from exploration, and the end of all our exploring will be to arrive where we began and to know the place for the first time. And indeed, we may know a lot more about this place for the first time. Thank you very much. So I hope I provoked you enough to have a discussion on all those different issues. Yes. So the question was, do I believe in my life or a semblance of life after my death? And here, as a true scientist, I will have to dissect your question. First of all, you're talking about life, but not in the same sense in which I was talking about life, biochemistry. And second, I need to define death. Death in physics is easily defined. It's the achieving thermodynamic equilibrium. And indeed, biochemical system which is in thermodynamic equilibrium, meaning nothing is happening, no energy is being exchanged, is exactly what we call a dead system. But you probably know that most of my body is not me, or is me, but is not my DNA. Is the microbiome, as we call it, the microbes that coexist with each one of us and which are very personalized and which essentially make us humans not good examples of what we would call life if it's a self-sustaining system. We're not self-sustaining systems as individuals, even as a species, because without those microbes, we cannot even survive for an hour or two. So what happens when we die is that microbiome doesn't. So how do you define my life after? I'm trying to be kind of dancing around your question maybe here. But I actually want to turn your question. So the answer to your question is obviously, I'm sorry that my brain is going to disintegrate, because that's where a lot of the things which I hold near and dear to my heart are. The memories and what I know about my closest friends and family and everything that I love. But death of a biological system and life in all those different incarnations is a very much deeper question that our language even allows to discuss. And I want to point out this because this was one of the reasons why it was so difficult for me to write some of the chapters of this book, because I didn't know how to use the language, apart from being Bulgarian, and my mother tongue is Bulgarian and Greek. I think we don't have yet the language to describe those new horizons that we are reaching, especially in synthetic biology, because we'll have to redefine a lot of the things which we call life or living, or what is living versus alive, and what is death then. I don't think I answered your question, but I hope it was worth it. Let me try to repeat the question in a short way. So, given that it took billions of years for the evolution of the biosphere, life on Earth, what can we hope to learn in just a human lifetime, which is less than a fraction of a nanosecond compared to all that in the lab or in? Well, we have learned quite a bit about the universe, which is 13 billion years, and a lot of things have happened between the first stars and even before the first stars and today. And we've learned it again in essentially 2 human lives worth, the beginning of 20th century to the present. And most of it we learned in literally the last 20 years since I was a student. So at least there is a feasibility example there. Maybe we can learn something. But let me be a little bit more philosophical about it. I don't think we'll learn the answers to all those big questions. What is the origin of life on Earth is especially difficult because it's also a historical question. Even the question of what are possible chemical pathways from chemistry to life is a huge question. I don't think we'll answer that anytime soon, the same way as we still haven't answered most of the basic questions about the universe and certainly about its genesis. So I think what we are trying to do here and what we're excited about doing as scientists are just trying to take a few steps in the right direction. And the realization recently has been that the people who have been taking small steps in the right direction in astronomy and planetary science, independently of the people who are doing that in chemistry and molecular biology, can learn a lot more if they work together. And so from a very societal point of view, yes, we can learn a lot if we work together in those different disciplines. But basically, again, the question is, can we learn something about the chemistry that drives one or another of the functions we know are very special and almost miraculous about life, without necessarily answering the big question all at once? I think if we manage to answer the question about alternative biochemistry, that is, even if we know that there is one alternative, one non-trivial alternative to the biochemistry which we have on Earth, there is a huge difference, as my friend Jill Tarter from the SETI Institute likes to say. There's a big difference between 1, our civilization, and 2, because that leads you to much larger numbers. But the same is true for biochemistry. We only know of one. In the moment we know even of the second one, we've actually solved the problem in a big way. The question, again, to repeat the question, how close are we to discovering such a building block? I think you're probably referring to the minimal cell. This has been a big effort for, as I said, 40 years. There are a lot of illustrious predecessors, big people of chemistry and molecular biology who have tried this mostly top-down, meaning reducing what we know about life. And that's why I said it failed, and it has failed so far, and we even understand why it has failed, and it's a good thing when we learn something in the process. What the people who are building it from bottom up are doing now are trying to complete the design of one element which is central to a self-replicating chemical system, and that is the ability to take a molecule which carries information, that stores some sort of information. Of course, I'm trying to say generally instead of saying taking DNA or RNA with genes in it, and translate this into molecules which build structure, which we call proteins. That's a little machine or molecular group is called the ribosome, and every single cell in every living creature has ribosomes which perform that function. And since the end of the 60s, people have been trying to synthesize ribosomes. They've been able to synthesize everything else, DNA, RNA, proteins, but they've never been able to synthesize a working ribosome. This was achieved in the past 2 years. And so there is a lot of hope and expectation that this now breaks the bottleneck and it will allow the creation of a true minimal cell, and we'll be able to study the properties of those basic functions without all the complications of the minimal microbes, which is the way people are trying to do it before. How can we get from the slight dimming, the mini eclipses, the transits of distant, very distant planets, to actually saying something about the chemistry? It takes a lot more than just the Kepler Space Telescope. So there you go. We're counting now in billions of dollars. Kepler costed $500 million. But actually, it's not that expensive, though it takes a big team effort. What you do is first you have to discover those planets, and transits are a great way to discover them. And I stopped there, but you actually learn a lot of more from transits than just discovering. The first thing is because they repeat, you get the orbit, the period of the orbit, and because we know how to measure masses of stars, with the old Johannes Kepler's laws, we actually know what the size of the orbit is. Distance from the star, and we know what the temperature on the surface of that planet is. Now, the second thing is when the planet is transiting on the face of the star, it's one disk covering a little bit of another disk. You know, the disk of the shining star, we don't see it, we see just a point of light. But the ratio of the two is what determines how much of a dimming we got. So that gives you now the size of the planet. So you know how far it is from the star, how warm, what's the size. Let's say it's the size of the Earth. Now you need to do more. Kepler can give you that much, the space telescope. You then go to another telescope and you measure this light from the star and its color and try to see whether that color is shifting back and forth ever so slightly with the same period as the period of the planet. If you manage to do that, and we've done it for more than 600 planets to date, then you know also the mass of the planet. That's another of Kepler's laws, but now with the addition from Isaac Newton. So you see the host of history in all this. But basically, now you will have the mass of the planet, how much stuff is in that planet, and its diameter, its size. That gives you the mean density. So at this point, that's how far we go. And up until 2 years ago, that was all we could do. We could say, this planet is rocky, that planet has a lot of gas, and this planet seems to have a lot of water, somewhere in between in mean density. However, since last year, because the mean density of water is in between that of hydrogen and rock. So there's a big difference between rock and hydrogen, and in between it's mostly water. But that's not enough, because we are talking about the surface, the atmosphere. I was talking about gases maybe from a biosphere which we could detect in accumulating in the atmosphere. That requires a lot more. And again, as I said 3 years ago, we didn't know more than what I just said Kepler could give us. But then one of my colleagues here up the street, Dave Charbonneau, managed to discover one super-Earth which is very close to us. And with the largest telescope that we already have on Earth, a few of the younger colleagues that we have managed to measure the color of the light coming from that planet. And you could tell from that light that the atmosphere had some water, had some carbon dioxide, and had some methane. So we can actually do that. We've done it already once. So this is the steps which we take in order to discover, understand, and then measure the chemistry on the surface of a planet. So I would predict that in the next 10 years we'll get much better at it, because it took us less than 10 years to get to where we are. And we will be able to do a lot of that. In fact, that's one of the motivation I personally have to go and talk to my colleagues in chemistry and biology for help, because I'll be awfully embarrassed in 10 years from now if we have those beautiful chemical portraits of planets similar to Earth out there, and we have no clue how to read them, because the only thing which we know to look for is the life that we know here on Earth, and that's not the right way to go about it. Is how far or how close are these planets to us and how far or close we need to go in order to accomplish this. Is that fair? Yeah, we have planets which are the whole range. We have planets like the last one I just discussed, recently discovered SuperEarth, which is literally 30, 35 light years away from here, which is very close in galactic terms. And then we have the Kepler planets, which are hundreds of them and thousands of candidates already, which by design are further away. Kepler was designed to find many and give us the fraction of planets in the galaxy. So we needed to find many. And so we are looking somewhat further away from the Earth. And the range there in the planetary systems that we discover is that they are between 500 and 3,000 light years from us, away from us. Still in the general local neighborhood of this part of the galaxy, the Milky Way galaxy. Now, in order to do what I'm hoping to accomplish here, to get the chemical signatures of such planets that have interest to us, the smaller ones, you definitely have to come closer. You have to discover the planets which are right next door, like the single example that we have already. You have to discover many more of those. And for that, we need a telescope which is different from Kepler. And people already working on designs for those and how to go about doing this. And I think now that we know that the fraction of those planets is fairly large, it makes sense that we'll discover a lot of nearby planets. So this project is doable, it's feasible, as opposed to maybe 10 years ago when we actually didn't know how common these planets are, and this project might not have been as feasible as it appears to be now. So the question, again to repeat it, is that we don't only have a diversity of planets out there, but also diversity of parent stars. For example, smaller stars, like the example of this recent nearby one, is a very small reddish star with a very different light shining on the surface of the planet. And then couldn't we use those conditions or recreate those conditions in a lab and study how the biochemistry which we know would react to that? Yes, indeed, that is the case. And the conditions that you would find on the surface of a planet would depend not only on what is the history and the makeup of that planet, but also on its parent star. And that's particularly very important for planets with conditions similar to Earth, because that determines what is the balance between, say, ultraviolet light versus, say, heat that such planets get. Ultraviolet light has a particularly strong effect on large molecules, as we know from having to use sunscreen. But seriously, it actually affects the chemistry, both of the atmosphere and of potentially what happens on the surface. So this has to be accounted for. Now, I also would use your question to make another clarification here. We tend to think of the surface of the Earth as being a very diverse set of environments. You have the oceans, the continents, you have ice, you have deserts, hot, cold, you have places like Yellowstone, which are full of sulfur, and you have places which are just the opposite. You then think about Mars and Venus, and you say, well, doesn't this cover all the diversity that is out there? And what we are learning is that this is probably not necessarily the case. That is, planets like the Earth, SuperEarths, this whole family, which are terrestrial, end up having one of several global cycles which determine the global conditions of the atmosphere and the surface of the planet. That is the hypothesis which we have now. And if from that perspective, what we see in the solar system is essentially just one, maybe two examples of what is possible out there. And then that means that if we want to really study alternatives to the biochemistry on Earth, we should understand what the alternative planetary environments are out there and try to start our search of pathways from there. And this is one of the goals of this big research project, is to take that information from the exploration of planets outside the solar system, understand the geochemistry, and then try to use that in order to understand what would potentially be a signature for life. Because if we were to be offered that gallery of planets today, the only thing which we could maybe see and be able to interpret is a carbon copy, literally, of our biosphere here on planet Earth. And that's not a winning strategy. So thank you very much for this.